Hello, I'm Alexander, founder and CEO of Code Wireless Communications. I'm in Telecommunications Engineering Laboratory at Institute of Telecommunication Systems of National Technical University of Ukraine, Kyiv Polytechnic Institute. And this is the second episode from video set about company technologies. And today I will tell you more about physical layer encryption and multi-user interaction of our modems.
Let's start from physical layer encryption basics. Generally, this is a set of arrangements that complicates data reception process on unauthorized devices. In other words, unauthorized devices can even acquire binary or memory data from received signal that is physically encrypted and it is recognized as noise or interference. Also, it should be noted that physical layer is taken from OSI model of telecommunications. Thus, physical layer encryption not only encodes data, but also forms modulator and demodulator. There are two types of physical layer encryption. First, for devices that are located in equal signal propagation conditions. For example, simple modulation or K methods, ASK, FSK, PSK, QAM, or FDM, and most advanced pre-coded OFDM. Second, for devices that are located in positions with different signal propagation conditions, or operate in channels with high fading. For example, beamforming or space-time block coding for MIMO. But given methods are not widely used due to such reasons. For the first type, pre-coded OFDM is not very different from common encryption at higher OSI layers which are widely used. And for second type, all these techniques are more often used for establishing of multi-user access and compatibility than for specific data protection. But I found another approach that really works as encryption. Company physical layer encryption technique belongs to first type and based on direct sequence spread spectrum CDMA technique. Common DSSS CDMA uses Walsh, Gold, Kasami codes for data transmission. Also another modern complementary zero correlation zone or large area synchronous codes are considered to use in future CDMA systems. So there are only a few code sets that can be used in CDMA for physical layer encryption. But I found the way how to create almost infinite quantity of orthogonal code sets from arbitrary numbers. Thereby, the arbitrary number that specifies the sequence set is the key for physical layer encryption, and these sets are quasi-orthogonal to each other and can be used in DSSS processing schemes. Also, the rule of generation of limited number of spreading sequence sets with good correlation and low mutual interference has been created, and for a spreading factor of 1024 that is used in our modems, number of sequence sets is more than number of possible devices in IPv6 network. Herein, probability of significant mutual interference or sets overlapping is lower or equal than bit error rate in AWGN channel. Thus, presented technology enables to generate unique modulator and demodulator for the DSSS CDMA scheme from arbitrary number or key, and it can provide unique physical layer realization for each or all possible devices in IPv6 network. Such technique cannot be realized by another usual encryption schemes at higher layers of OSI model, so this is real physical layer encryption, and it is classified as polyalphabetic cipher. Additional mixing of serial numbers of sequences in the set can be used to increase crypto protection. In conclusion, general features. First, identification. Receiver can identify transmitter if it knows some pool of keys, and you can transfer data to a specific device. Second, information protection. You cannot even receive signal if you do not know key. Third, ability to provide resistance to interferences due to its spread spectrum nature. And as consequence, it can provide independent multi-user interaction or wireless network separation when joint frequency resource is used in the same area. All these features are provided by technologies of MMBOK encoding and asynchronous DSSS CDMA data transmission that help to achieve highest efficiency and belong to the company. Thus, several CDMA networks can be deployed in some limited area and use same frequencies at the same time, and devices in different networks can operate independently or asynchronously, but in one network synchronously as usual CDMA scheme. So let's see how this all really works. But first, a few words about testbed. I will use Uptest Research B200 SDR and GNU Radio version 3.7.11 and network of our modems. I begin from trials of asynchronous data transmission in independent links that use different spreading sequence sets because multi-channel Emery B-orthogonal chain utilizes whole sequence set for this. First case of two links with equal signal power at both of receivers' input because they are located at the same distance from transmitters. These are transmitters. This is GNU Radio that displays time and frequency domains of signal, and this is SDR. And these are receivers. Distance between receivers and transmitters is near 1 meter. Each pair of modems is precoded with their own encryption key. Turn on the first link and observe its envelope and spectrum. First transmitter works. Signal is well observed as in time as in frequency domains. On the corresponding serial port terminal, we can observe that the test data transmission is successful. Turn off the first and turn on the second link. Signal is radiated and second transmitter works. Signal well observed and has equal power and the same frequencies as the first link. At second serial port terminal, we can observe that the test data transmission is also successful. And now it's time to check. Does our technology of asynchronous multi-user CDMA work? Turn on first link and both of transmitters are operational. Signals overlap each other, frequencies the same, and at serial terminals we can observe that the data is transmitted in both of links. They are operating well. I clear terminal screens to be sure. Yes, data is transmitted in both of links at the same rate. Now I try to show GNU Radio display and terminal screens more closer. As we can see, both links occupy the same frequencies and in time domain they are overlapping. Despite the fact that pause between packets is equal to packet duration, TDMA is not applied here because signal transmission in both of links been conducted asynchronously. GNU Radio shows that power in second link is slightly less, but trial conducted not in anechoic chamber and SDR antenna polarization not matched. And the main task here is to show that the signals are really transmitted asynchronously at one frequency. Then turn to terminal screen. At different terminals we can see different data from both of receivers. Simultaneous data transmission is successful. Awesome! Asynchronous transmission really works! Let's test other practical cases for this technique. It is well known that power equalization between transmitters is critical in multi-user CDMA. Let's check how much it's significant in this case. Special testbed is created where transmitter of first link is located at 6 meters from receivers and second link transmitter is located at 1 meter from receivers. Receivers are located in one position close to each other. Thus, around 15 dB of power difference between links at receivers is established. Both of links are operational. Here, signals from both of links overlap each other and frequencies are the same as in previous test. Sure, the power difference can be increased, but then qualitative reception from a weaker transmitter cannot be guaranteed, because 15 dB gain is worst case and a real processing gain for all possible sequence sets of spreading factor of 1024 that is used in this case. For sure, processing gain can reach 30 dB respectively to this spreading factor in some case, but generally for wideband interference processing gain is equal to square root of spreading factor. Then turn to terminal screen. Data is transmitted successfully in both of links at the same rate. The operability of technology in this case of unequal signal power is proven. Here, signal from transmitter with another key of physical layer encryption is recognized as interference, not a signal from other channel, and is suppressed in receiver. And this is the reason why power equalization not necessary in this case. So, the signal from a more distant desired transmitter can be received even if there is a closer transmitter with another key. And we can conclude that independent CDMA networks will work in some area without additional arrangements due to their spatial location. Another practical case answers the question: how many CDMA links with different physical layer encryption keys can operate in one area and under the same propagation conditions? Let's try to establish communication in 8 links. For this, I will use 8 transmitters with pre-coded keys and 1 receiver. All transmitters radiate different phase data asynchronously at one frequency. I will change key in receiver to connect to different links. In this case, one signal is desirable and 7 other act as interferences. All transmitters are operational. Now I show you signals in time and frequency domains. At time domain, we see relay mass. Separate signals are not recognizable, but located at one frequency. Then I turn to terminal screen, where I can show you results of test of receiving process. Now receiving from 8th transmitter or for 8th key is established, and data receiving for this case is successful. But what about other channels? I need to stop receiving and change key. I'm entering command, choosing first key, and download it to modem. Starting receiving process of test packets. Yes, receiving is successful. Errors are present because forward error coding is not used here and seems that first transmitter located in worse conditions. Then let's check receiving from second transmitter. I have to do the same actions as for the first key. Stop receiving, entering command, choosing second key and downloading it to modem. Starting receiving process. Yes, in this case receiving is also successful and has better quality. Now I switch in testbed to receive signal from the third transmitter. As previous, receiving is also successful and quality is excellent. Finally, check data receiving from fourth transmitter. As previous, receiving is successful, so this is like frequency changing, but really the same frequencies are used. And 8 links is not a limit for this configuration. So, what have we got in total? Usage of given technology enables to run several independent DSSS CDMA networks, or links, that are powered by different physical layer encryption keys in one limited area and on the same frequency without additional arrangements. The next part of this video is devoted to multi-user interaction inside one common synchronous DSSS CDMA network that uses one spreading sequence set which is created by unique physical layer encryption key. Such network consists of one master device that initiates transmission process and several slave devices that simultaneously receive from or transmit data to master device. All devices in network can achieve master or slave role. Multi-user data transmission is powered by multi-channel MRB orthogonal chain that belongs to the company. Another interesting feature that all transmission processes will be done without synchronization channel and strict synchronization between transmitters and receivers, as in common DSSS CDMA, but power equalization is still necessary. Let's start trials. In the first case, master device transmits data to two slave devices. Master device is fed by UART, where TDMA is used. So, master device transforms TDMA data transmission from UART to CDMA in air when data is transmitted, and CDMA to TDMA when data is received. Turn on cyclic test data transmission via two CDMA channels at master device. Then, turn on test data receiving from two CDMA channels at one slave device. At terminal, we can see that 16 bytes is transmitted and is a hex symbol from 0 to B, and for zeros, average data rate in two channels 200 char per second. Then I turn off this receiver and turn on two other receivers that receive data from channels separately. First receives data from first channel and second from second channel. At terminal that is related with second device, we observe even numbers. At terminal that is related with first device, we observe odd numbers. CDMA to TDMA transformation is successful. Average data rate in each channel 100 char per second. Multi-channel transmission from one master device to two slave devices is successful. Then turn to the second case. Here, master device acquires data from two slave devices. All transmission processes are conducted without pre-synchronization or system synchronization as before. Master device sends acquiring data request and slave devices transmit preconfigured amount of data to master device in response. Signals are added at master device with small out of sync of chip and decoded. So, let's see how this happens. For beginning, I will acquire data from two devices simultaneously. The master device is preconfigured to receive data of 3 bytes from each preconfigured slave devices, 6 bytes in total. Entering command. I've got data. Turn to terminal. Here we can see these 6 bytes. Then I turn off second slave device. Entering command for request. Turn to terminal and we can see this data. As the places of bytes from second device we can see junk data, but bytes from first device are received. Then I turn off first slave device and turn on second slave device. Entering command for request. Turn to terminal and we can see this data. Now we see junk data at the places of bytes from first device. Good visual demonstration of TDMA, isn't it? Multi-channel data receiving by one master device from two slave devices is successful. Now I will show that I can get the same result from more distant devices that are spaced apart. Entering command for request. Data is received. Entering command another time. Turn to terminal. Yes, successful, the same result. Operability of this technique is approved. So, what have we got in total? The new method of physical layer encryption that based on DSSS CDMA has been realized. It enables to implement different physical layers which create a very weak interference to each other for all devices in IPv6 network. 8 independent DSSS CDMA networks that based on spreading factor of 1024 and use multi-channel Emery bi-orthogonal chain can operate on the same frequencies within the one area of radius of 50 meters. Independent DSSS CDMA networks can work asynchronously without any arrangements. Devices inside one DSSS CDMA network operate synchronously but without synchronization channel. They are led by master device. This is all for today. At next videos I will show you more trials of real applications of presented technologies. Especially attention will be paid to advanced network services and solutions. I think this video was interesting for you and helps you to understand spread spectrum technologies more deeply. If so, please support it by like and your subscription to this channel.